Hello everyone, I hope everyone is doing good. We are gonna start our next topic today. We will be moving from MOSFETs to bipolar junction transistors, BJT. It's a new chapter of the book, chapter number 6. Again, we will cover the basic topics, the physical structure, its operation of the bipolar junction transistors. In this chapter, we will see how we can operate these transistors in DC circuits. And then we will again move back to chapter number 7 and discuss the topics of the amplifiers that are related to bipolar junction transistors, and we will study how we can use these bipolar junction transistors or BJTs in different amplifier configurations, right? So we have a bipolar junction transistor, BJT. Okay, so let's start with that. So we have seen that these transistors are usually three-terminal semiconductor devices as compared to a two-terminal diode. MOSFET is a three-terminal device, right? So we have a source, gate, and a drain terminal. We also had a fourth one, the body, too. But that was usually used to reverse bias the junctions and to operate them into the cutoff mode. Okay, so our diode is a regular PN junction, and that's a two-terminal device, and our bipolar junction transistors are also regular PN junctions. They much more closely related to the diodes. You will realize that soon. And they are three terminals. We can make them by combining the two PN junctions together. We're going to discuss that shortly. We have already seen this thing. They can be used in many applications. We can build amplifiers. We discussed that in detail. They can be used to make logic gates, memory units, microprocessors. You are going to learn more about microprocessors and how we can use these transistors, develop different logics in digital electronics course. We talked about this basic principle, especially related to the MOSFET, if you remember, right? So first we apply a gate to source voltage to induce a channel. Then we apply a drain to source voltage. So the voltage is applied in between two terminals, and the current will start to flow. So we can use this as a switch. We have two major types of the semiconductor devices or transistors. We already talked about MOSFETs, and now we are starting to talk about bipolar junction transistors. Again, a very quick comparison in between both of these in terms of its applications. And we already discussed that for the MOSFETs. MOSFETs are more widely used in the microprocessor industry because they are very small. Their fabrication process is slightly or relatively simpler as compared to bipolar junction transistors, and they require very small power to operate, right? So we need more battery lives, of course, to operate our laptops, smartphones, and all of our regular other electronic devices based on microprocessors. So that is why they are more favorably used to develop and fabricate these microprocessors. Now, so we are using MOSFETs for more integrated circuits. However, so what is the application of the BJT? BJTs are more relevant for applications that require very high frequency operation or very high current driving circuits. This is where we use the bipolar junction transistors. Interestingly, we can also develop, we are not going to discuss this thing in detail in this course, but just to give you an idea, interestingly, we can also develop something that is called as a bi-CMOS circuit, in which we combine the bipolar junction transistor and the MOSFET in the same circuit. And the advantages of such bi-CMOS circuits are, it combines the advantages of both of these devices. For example, for the MOSFET, a very high input impedance and low power operation. And for the BJTs, very high frequency operation and a very high current driving capability of the BJTs. So we can also develop this again by CMOS circuits to take advantages of both of individual advantages of both of these transistors together. Again, we will not discuss this by CMOS in detail in this course, but just to give you an idea to discuss for future reference. Okay. So let's start with the kind of delving more deeper into the bipolar junction transistor. Okay, so here is the structure of the device or a bipolar junction transistor. Here is an NPN BJT bipolar junction transistor and an NPN. Again, it is a three-terminal device. One terminal is this emitter, other terminal is base, and the third terminal is collector. And as you will realize that this bipolar junction transistor is three extrinsic semiconductor regions combined together, right? We have an N-type emitter, P-type base, and an N-type collector. So when I say an NPN transistor, this means that the first N is for emitter, the second one is for base, the third one is for collector. So our emitter is N-type, our base is P-type, and our collector is N-type. Just kind of for illustrations and how it is conventionally used. Okay, now another thing that you will realize from here is that, okay, so we in order to give the signals in or out, we also have this contact pads, right? Metal contact pads with all of three terminals, with all of these three terminals. Right, so we have three regions for emitter, N-type, base, P-type, and collector N-type for this NPN transistor. Similarly, you can also see a PNP BJT. Now P is emitter, N is base, and P is collector again, EBC, right? So you have an emitter, base, collector, P-type emitter, N-type base, P-type collector. So this is how your three junctions are, three semiconductor regions are for a bipolar junction transistor. Another interesting thing to look over here is the two junctions that are being formed by combining the three semiconductor regions. One is this junction in between emitter and the base. This is known as EBJ, emitter base junction. The other junction is this, which is in between collector terminal and the base terminal, in between these two terminals. So we have a collector base junction. Similarly, over here, we have an emitter base junction and a collector base junction, right? So it is three extrinsic semiconductor regions combined, emitter base and junction, emitter base and collector. The second thing, it forms two PN junctions, emitter base junction and a collector base junction. Okay, so we have three terminals, emitter base and collector, and two junctions, emitter base junction and collector base junctions. And now we will realize that the way that we bias these junctions, we can bias a PN junction as a forward bias and reverse bias. So the way that we will bias these junctions, we can operate these transistor into different modes of operation. Okay, so let's talk about it. Modes of operation. The way, three different ways that we can operate this transistor. So we can operate the transistor in a cutoff region, in the something that is called an active region, and a saturation region. And here's a table of how to bias those junctions and how to bias an emitter based junction and a collector based junction to operate in two different modes. For the cutoff region, it needs to be biased. Both the junctions should be reverse biased. For an active region, emitter based junction should be forward biased, collector based junction should be reverse biased. And for saturation, emitter based should be forward biased, collector based should be forward biased as well. So one important distinction that we need to make over here between the MOS-FET and the BJT is the active and the saturation. Please remember that for the MOS-FET, we had a cutoff region, triode region, and the saturation region. Saturation region was also known as the active region. However, over here, for the bipolar junction transistor, at least this is how it's in the literature, that we have a cutoff region, an active region, and a saturation region. Again, active and the saturation regions are not the same. In a MOS-FET, active and the saturation regions are exactly the same. Okay, so coming back again to the bipolar junction transistor, again in the cutoff mode, transistor is not operating and both the junctions are reverse biased, no current is flowing. In the active mode, we will use the bipolar junction transistor as an amplifier. For the MOS-FET, we were also using the active region to operate that as an amplifier, but the active and the saturation means the same thing over there in the MOS-FET and not here in the BJT. Third mode of operation is a saturation operation, in which we can use a BJT or bipolar junction transistor as a switch. In between, we can switch in between a cutoff mode and the saturation mode. For a MOS-FET, the regions of operation to operate MOS-FET as a switch was cutoff and triode. Over here it is cutoff and saturation. And saturation and active are two different things in a bipolar junction transistor again. Another important distinction for the in terms of modes of operation in between the BJT and the MOSFET is the charge carriers that are involved in the current conduction process. Right? For an NMOS, if you remember, we induced an N channel, and we have electrons as majority charge carriers constituting the current conduction. For a PMOS, we induce a P channel, and we have holes that are involved in the current conduction process. We will realize that in a bipolar junction transistor, whether it is an NPN or a PNP transistor, both electrons and holes will participate in the current conduction process. And this is the reason that is why it is known as a bipolar junction transistor. Okay, now let's talk more about its actual operation. So how do we operate the transistor and how does this current flow? Okay, so let's consider the active mode. Again, going back to the table, active mode is emitter based junction is forward biased, collector based junction is reverse biased. Okay. All right, so this is where our NPN transistor is, right? So this is NPN. So we have an NPN transistor and our two junctions again. This junction is emitter based junction, which is forward bias, and this is our collector based junction, which is reverse bias. Now to forward bias a PN junction, P-type material should be at a higher potential as compared to N-type. So we ended up biasing this emitter based junction with the supply VBE, and this will be forward biasing it because the P-type base is at a higher potential as compared to the emitter, and of course it needs to cross this barrier potential for the current to occur. Now if we look at the collector based junction, is whenever a PN junction will be reverse biased, then the N-type is at a higher potential as compared to a P-type, which is exactly the same thing over here. Over here, our collector based junction is biased by this power supply VCB, in which our collector, which is an N-type, is at a higher potential as compared to a base, so our collector based junction is reverse biased. Okay, so we have a forward biased emitter based junction and a reverse biased collector based junction. So when we forward bias and this is what I just said. Okay, so when we forward bias the emitter based junction, our current will flow across this junction, right? And so let's look at the currents in more detail. So important thing, when we are going to this forward bias this emitter based junction, our current will flow, but it will constitute with two components. So one of the component will be these electrons that will be injected from the emitter to the base, and the other component will be these holes that will be injected from the base to emitter. Now again, important thing over here is in the N-type material, right? You know that we have a lot of these electrons, and in a P-type material we have a bunch of these holes in all of these extrinsic semiconductors. Okay, so when we forward bias this junction where our base is at a higher potential as compared to the emitter, these electrons will start to flow from the emitter to the base. This will be known as injected electrons from the emitter to the base. And at the same time, our free holes from the base region will start to move from the base to the emitter, right? So that is why you can see that the direction of the emitter current is coming out of the emitter terminal. Another important distinction that is to be made over here is that the current, so it is composed, the emitter current is composed of two different components. So one is these injected electrons, the other one is this injected holes. So looking at the value of this current, or the amount of these charge carriers that are flowing, the amount of the electrons or the number of the injected electrons from the emitter to the base is much more higher as compared to the number of the injected holes from the base to the emitter. And that is why, and we can see that how we can make sure that this will be happening. We will realize that what's the benefit of it later. The way that we can make sure that this is happening, because our base is the width of the base, this width of the base is very small as compared to the width of the emitter region. Second, our emitter is much more heavily doped as compared to the base. So in terms of the availability of these majority charge carriers in the N region, we have a lot of these electrons available and very comparatively small number of holes available in the base. Right, okay, so this is what we talked about. We can fabricate a device with a heavily doped emitter and a lightly doped base. So we have a high density of electrons in the emitter and a low density of holes in the base. Right, so when we forward bias this junction, a lot of these electrons in the emitter will flow from the emitter to the base, and we have a small amount of the holes that are present in the base that will start to flow from the base to the emitter. Okay. So let's look at all the currents in more detail. Right, so this is what we have just talked about, that our emitter current has two components again: injected electrons from the emitter to the base region and injected holes from the base to the emitter region, right? And our electron component, which is the electrons that are injected from the emitter to the base, is much larger because of the doping and a bigger width of the emitter regions as compared to this hole component. Okay, so our emitter current has two components, and the electron component of the emitter current is much more significantly larger or dominated as compared to the hole component. So what will it be proportional to? So if you remember the PN junction, the chapter number 3, the diode section, you will remember that the current that will flow is proportional to the scaling current and then the exponent of the biasing voltage to the thermal voltage, right? So the biasing voltage to this junction, PN junction, over here is this emitter base junction, or the VBE. So we can say that our current that is flowing from the emitter to the base junction is proportional to e raised to power VBE, the biasing voltage of the emitter to base junction, to the thermal voltage, right? So it will be proportional to this. Okay, so let's see more details about this current that is proportional to EVBE over VT, or this current, right, that is flowing in between, or the number of the electrons that are injected from the emitter to the base. So let's discuss that more. Let's discuss this first component more. Electrons that are injected from the emitter to the base. So what will happen to those electrons? Now, as these electrons that are injected from emitter to the base, now we know that there were some holes that are available in the base region. Some of these holes were injected back from base to the emitter. However, some of these holes will be recombined or will be combined with the electrons and gets neutralized. The process is known as a recombination process. So we have a bunch of these electrons that gets injected into the base terminal over here. Some of these electrons combines with the holes in the base region and neutralized by a process known as recombination. Majority of these electrons will be swept across the collector to base junction here, right, and will move all the way to the collector region. And why is that? Because our collector to base junction is reverse bias. Again, our collector is at higher potential and we have a lot of these electrons that are flowing. So our electrons, some of these electrons were kind of lost or in the recombination process in the base region. Rest of the electrons were swept across the collector to base junction through the collector region. Since our flow of electrons over here is in this direction, so our electrons, our collector current will be flowing into the collector terminal. Okay. So this is what we just talked about. So this current component in which we have these electrons that were injected from the emitter to the base, some of these will be combined with the holes and neutralized in a recombination process. Again, our base was very thin and very lightly doped, right? And then we have our collector to base junction was reverse biased. So that is why they will be swept across through that junction and move to the collector terminal. So collector base junction is reverse bias. These electrons will be swept across the collector base depletion region into the collector terminal, and this will constitute the collector current, right? So again, the point to be noted that the collector current is the same as this collector current. What is this collector current? This collector current is the same as the majority charge carriers that were injected from the emitter region, right? So this is what constitutes the collector current. So these injected electrons again comes to the base terminal or base region, where some of these are lost in the recombination process. Rest of them were swept across through the base collector to base junction to the collector region. So so the value of this collector current again will be proportional to the component of the biasing voltage to the thermal voltage, right? And what is this biasing voltage? This biasing voltage, now again, since the collector current is the same number of same electrons that is coming from the emitter region, right? So that constitutes the collector current. So again, our biasing voltage over here is again VBE. Right, okay, so collector current is carried by the electrons that reach the collector current, and we talked about the direction of the current flow. Okay, so again, our collector current is proportional to the scaling current, if you remember the PN junction, and again it is proportional to the VBE. Again, why this biasing voltage? Because the electrons that were coming from the emitter to the base were the same electrons that is moving to the collector terminal and constitute the collector current. Okay. All right, and if you remember that this IS is something that is called as a saturation current or also a scale current, right? Because this will scale to the size of the device. We're gonna study that in more detail today. And this also depends, again, this is a transistor parameter. Okay, now let's look at the base current. So what is happening at the base? Base current is also composed of two different components, right? Over here, okay. Now coming to the base current now. So we have seen the collector current, now let's come to the base current. So our base current is, two things are happening over here. So the one base current is this IB1. When we forward bias the emitter to base junction by this power supply, we have these holes that were injected from the base to the emitter, right? So this is IB1, this is one component. Our second component is this IB2. So what is happening with this IB2, or what is this IB2? So we know that what is happening in the base region is some of this is IB1, which is holes injected from the base to the emitter, and some of the holes were being lost in the recombination process with these injected electrons from emitter to the base. So some of those holes will get lost. So in order to replace those electrons or those holes, the holes were drawn from the external circuit into the base. So that is why this is the direction of the base current. So some of these holes were drawn from the external circuit, right? So the amount of that current or the holes are the same amount of the electrons that were lost due to the recombination process. Okay, right? So our IB1, the first component is the holes injected from the base to the emitter. Again, that was proportional to the emitter to base voltage, or the junction, the voltage that we apply at the junction, right? So IB1 is also proportional to VBE over VT. Yeah, and then we have a IB2 current, which is the holes which were supplied by the external circuit to replace the holes that were lost because of the recombination process, as we talked about, right? And since we know that the number of the electrons that were injected into the base, right, so those were some of these electrons were lost into the recombination process, and the same number of the holes are being drawn from the external circuit, so that should also depend on the same biasing voltage, VBE. So that is why your IB2 is also proportional to VBE over VT. Okay, so the total base current is now the summation of these two, IB1 and IB2, and since both of them are proportional to VBE over VT, so the total base current will also be proportional to the base exponent of the voltage at the junction to the thermal voltage. Now, as we may realize that just by looking over here in this figure, that the concentration of these holes, or the amount of the current of the base current, should be very small as compared to the amount of the collector current here, right? We have a huge number of these electrons that were initially injected from the emitter to the base. Some of these electrons are lost in the base in recombination, and the rest of these electrons constitute the collector current. So we have this very high collector current. as compared to the base current, which was very small to start with because of this IB1, very small number of holes that were injected from the base to the emitter, and some of these holes were drawn from the external circuit, which is the same as the number of the holes that were lost in the recombination process. So our base current would be just a fraction of this collector current. Okay, so our base current should be a fraction of this collector current. So we can see that we can represent that factor by a factor beta. So I can also write beta as IC over IB. It's a ratio of the collector current to the base current. All right. Okay, so let me rub this out so I can explain this. All right, so our beta is IC over IB. Okay. And we know that the collector current IC was equal to the scaling current e raised to power VBE over VT. So we can replace that over here. So this is your collector current to the beta is IB. So this is coming from this equation. So one important consideration looking at the beta, now we can see that this beta is very interesting because this is the ratio of the collector current to the base current, right? And we can say that this is a gain factor or this is a current gain factor. And if we look, and we're going to discuss this much more in detail, that this is the gain factor that we will obtain when we are going to have a common emitter configuration. If we have a emitter terminal as common in between input and the output, then we can see that the ratio of the currents will be the gain factor over here, right? So this beta will be a common emitter gain current or a common emitter current gain. This beta is a transistor parameter, and for NPN transistor, beta is in the range of 50 to 200, but it can also be very, very high, up to 1000 as well. And beta is known as the common emitter current gain, since beta is equals to IC over IB, collector current to the base current when the emitter terminal will be common in between input and output. So when we will discuss how to develop these amplifier circuits using these bipolar junction transistors, this thing will become much more clear. Now let's look at the beta slightly more. What factors does this beta depends on, right? So if we look closely at the beta over here, it is a ratio of the collector current to the base current, right? So if we decrease the collector base current, the beta will increase. If we increase the collector current, the beta will increase. Right, so our base current and the collector current. So the base current depends on the base and the collector current both depends on the width of this W, the width of this or the thickness of this base region, right? So if we have a smaller thickness, this means that our total number of the holes in the base region will be smaller, keeping the doping concentration the same. And if that is true, this means that our base current will be smaller, and the number of the holes lost in the recombination will be smaller, and our collector current comparatively will be higher compared to the base. So by working on the width of the base, by reducing the width of the base, we can increase the beta value. The second important component is the doping levels of the emitter region and the base region. If our emitter is more heavily doped as compared to the base region, our collector current will be higher and the base current will be lower. And similarly, if we will try to make sure that the relative doping to the base region to the emitter region, if we can make this doping to be smaller, our beta will increase, right? So what we want essentially is that we want the doping of base should be smaller and doping of emitter should be larger, right? So if we have a base where that is very small, or we have a base that is lightly doped with emitter being heavily doped, or by making this ratio small, right, our beta can be very high. So these are the factors that our beta depends on. And for our modern transistors, this width of the base region is almost in the nanometer range, just to give you an idea. Okay, now, right, so again, as a summary over here, our beta is a common emitter current gain, depends on the collector current and the base current. They both are related to each other. So if we make the width over here, the width of the base to be smaller, and our concentration, doping concentration of the emitter is larger, relatively larger than the concentration, doping concentration of the base, then our collector current will be much larger as compared to the base current. And when that thing will be true, our beta values will be larger. And again, ideally we want beta to be larger because it's a gain factor. Okay, and this is a common emitter gain. We will discuss that in more detail. Okay, so let's talk. We have talked about the base current. We have talked about this collector current. So let's come back to the emitter current. Now, if we will realize over here, our emitter current, if I will look at the directions, right? So the emitter current is flowing over here. Our base current is into the terminal. Our collector current is into the terminal. So our emitter current over here is equal to the summation of the base current and the collector current. Right, so emitter current is the sum of the base current and the collector current, so we can just replace the values of both of them. We know that base current is the fraction of the collector current, IC over beta, and we also know that this IC is proportional to the scaling factor, VBE over VT. Now we can just replace these values into this equation and find the value of the emitter current. Okay, so we already know this thing, so let's just replace the value over here. So if we replace this value over here and then solve the equation, we can come up with this, right? So we have IE equals IC plus IC over beta. So you can also try and solve this if you want. So you're gonna have beta times IC plus IC, IE equals beta IE equals beta plus 1 IC, sorry. Okay, so beta plus 1 into IC. So you can also, so IE will be equals to beta plus 1 over beta IC, right? So you can easily drive this equation over here. Now you can also replace this value of IC into this equation to come up with a new equation of IC or emitter current, which will be equals to IE equals to beta plus 1 over beta into the scaling current e raised to power VBE over VT. You can also put it like this. Now we are going to develop an alternative expression for the emitter current as well, and that will be using this equation. Right, so we have this equation over here. Our emitter current equals to beta plus 1 over beta into IC. Now we can show this factor. We can take an inverse of this factor and replace that factor to be by an alpha over here, right? So our alpha over here equals to beta over beta plus 1, right? So if I will replace this thing by 1 over alpha here, I can see that my collector current will become proportional to alpha times IE. And why we did that, you will realize that again later as well when we will develop more amplification circuits. But just by looking at this equation again, I can see that over here alpha equals to IC over IE, right? So alpha is also if I will compare that to the beta, alpha also looks something similar. It's a ratio of the current values, right? So it's also a current gain factor, and it's a ratio of the collector current to the emitter current with a base common. So if we have a common base between the input and the output, our alpha can be known as a common base current gain. And again, this will be much more clear shortly, right? So here's an alternative expression of the beta of the alpha. So alpha equals beta over beta plus 1. We also derived it over here. Okay, so this can also be rewritten over here like this. IE equals, we are putting the IC value here, which is IC equals IS e raised to power VBE over VT. And this beta over beta plus 1 over beta here is equals to 1 over alpha, right? So I can easily rewrite this thing as IS VBE over VT, which is IC, and 1 over alpha here. right? Beta, yeah. So these are kind of alternative expressions. You can also, if you're gonna kind of rearrange this, you can also express beta as alpha over 1 minus alpha. So the important things over here, right? So alpha, like beta, alpha is also a constant and is one of the transistor parameters. Another thing over here, if you look at this equation over here, now the value of the alpha is always going to be very close to unity. Why? Because betas are usually very larger, right? So in last slide over here, we saw that beta is anywhere from 50 to 200 and sometimes even 1000. So if you have a very large value of the beta, then the ratio of beta to beta plus 1 will be very, very close to unity. For example, if the beta is 100, then 100 over 101 equals 0.99. So the beta will be almost very equal to a unity factor. Okay, so another important conclusion that we can draw over here, that for a very small change in alpha, right? If we looking, for example, you can look over here now. If you have a very small change in alpha, let's say 0.01, 1 minus 0.01 will be 0.01 over 0.99. The change in the beta will be very, very larger, right? Okay. So very small changes in the alpha will produce a very large change in beta values. And again, alpha is known as a common base current gain. And again, this thing will become much more clear when we will talk about different configurations, how we can use these bipolar junction transistors in different configurations. For example, amplifier configurations, common base or common emitter. These notations will become much more clear. Okay, now we have this one small topic before we will wrap up our lecture today, and this has to do with the distribution of the charge carriers throughout this NPN transistor, bipolar junction transistor. So we're going to talk about this figure in more detail. So assume two things. One, we are working with an NPN transistor, right? NPN transistor. Second thing, you can assume that it is being operated in the active mode, meaning that emitter base junction is forward bias, collector base junction is reverse bias. Another thing that we are assuming over here is that our emitter doping is much higher than the base. Although that is not to scale over here, because you can see that the width of the base is much higher as compared to the collector and the emitter. Usually emitter and the collector regions has a much bigger width as compared to base. So all right, okay, so the base has less doping or compared to emitter. Emitter is very heavily doped as compared to base, and base width is smaller. Okay, so let's look at that in more detail. So the first thing is, on the y-axis we have the concentration of the charge carriers. On the x-axis we have a distance, right? So we are starting from the emitter region. If I will draw this, right? So we have an NPN. So we are starting from this point to this point, and we're going to look at the charge distribution profile over here. So when we will forward bias the emitter to base junction, this region shows the depletion region. If we look at what we know, for an NPN transistor, when we forward bias emitter to base junction, we will have a lot of these electrons. A very high number of electrons will be injected from emitter to the base region, and then we are going to have these holes that will be injected from the base to the emitter region, right? And these are shown over here by these labels, that these are the holes that were injected from the base to the emitter, and this is you can say the concentration of those holes, and this is the number of the concentration of the carriers or the electrons that were injected from emitter to the base when the emitter base junction is forward biased, right? So this shows the holes that were injected from base to emitter, electrons that were injected from emitter to the base region. So these are the starting concentrations of those charge carriers. All right. Okay. So now we will see that what will happen in the emitter region. The concentration of the holes will decrease as they will be combined with the electrons. So it is going to follow this profile. And right at the start of the emitter region, the concentration of the holes will come out to be P and naught. And now looking at this concentration NP naught, which is again the concentration of the charge carriers that were the equal to the number of the electrons that were injected from emitter to the base region. Right, so this is proportional to this NP0, number of the electrons, or the concentration of the electrons injected from emitter to the base region when emitter base junction is forward bias, is proportional to, again, VBE over VT. We know that proportional to the biasing voltage and the thermal voltage, of course. And then it is also proportional to this NP naught, which is the thermal equilibrium value of the minority charge carriers electrons in the base region. Right, so this is proportional to two things. The number of the charge carriers, again, that were injected from emitter to the base region when the emitter base junction is forward bias, has to do with the biasing voltage, and the thermally equilibrium number of the minority electrons that were present in the base region. Right, okay. So the second important point that we can see over here, once we have these injected electrons over here, which came from emitter to the base region, what they will do is some of those electrons will be lost or by combining with the holes in the base region in a recombination process and neutralizing it. So we are going to lose these electrons. Right, and then the rest of these electrons will be swept across this collector to base junction into the collector terminal, because collector to base junction is reverse biased. Right, so the concentration of these electrons will decay linearly, right? So ideally what will happen is the concentration of these electrons will decay linearly in the base region, as these electrons are constantly being swept across the collector to base junction because of the reverse biasing of that junction. However, this is an ideal profile, this linear decrease in the electrons in the base region. What actually happens is we get this kind of a dotted line or a concave shape. And why is that? Because some of these electrons are also being lost. We are not getting a linear decrease of the charge carriers in the base region. However, some of these electrons are being lost as well in the base region due to the recombination process, and that is why we get this kind of a more like a dotted line over here, which represents a higher loss as compared to this linear loss over here. Now, these electrons that were diffused from the base region to the collector region, let's call these electrons, or let's call this current as an IN. And how we can calculate this current IN is by using this equation. Again, you can also find out a similar equation from chapter number 3 when we were discussing the PN junction and semiconductors. So we can find out this equation by taking a slope of this linear line. Let's assume it to be ideal for now, considering that we have our base is very lightly doped as compared to the emitter. So the number of the electrons that were lost in the base will be very small and depends again on the doping concentration, right? For example, if the base would have been more lightly doped, this dotted line would have been more closer over here. If the base would have been less lightly doped, this dotted line would have been more over here. Right, this would have been even more over here because we're going to end up losing even more electrons in the recombination process. So we can find out the slope of this line, assuming the line to be ideal over here, right? Okay, so our current, this diffusion of these electrons from the base to the collector depends on the slope of this line. If I have to find out the slope of this line, so this is 0 minus starting point NP0 over X width. So this is the slope of this line minus NP0 over width. So the slope of dnpx over dx will be equals to this, and then we have these constant values related to the transistor, where AE represents the cross-sectional area of the emitter-base junction, Q is the magnitude of the electron charge here, Dn is the electron diffusivity, and W is the effective weight of the base. So these are all the transistor parameters in terms of the area of the junction, magnitude of the electron charge, electron diffusivity, and the effective weight. Again, you have seen this equation in chapter 3, so we are taking it as is. Okay. So this is the point that we already discussed, that rather than getting this linear decrease over here, we get this dotted decrease or a concave shaped decrease because of this recombination process. And this decrease in the concentration of these electrons in the base region will depend on the doping concentration, relative doping concentration in the base relative to emitter. So if our base is very, very lightly doped as compared to emitter, the more ideal linear curve we will get. Okay, so another important thing to look over here is this IN, the number of the electrons that were diffused from the base to the collector. You can see that this is proportional or equal to the collector current. This is essentially the same as a collector current except the direction. So I can also write that my collector current will be the inverse or minus of IN. And we know that this is the value of the collector current, which we derived earlier. Right, so this was our collector current. IC equals IS E VBE over VT. So this is the collector current, and we derived over here the value of the IN over here. So what we can do is now we can replace this value and derive another equation. Okay, so IN equals minus IC over here. So this is the value of the IN that I started with. You can also put this value of NP naught. Okay, right, so this is the equation that we ended up driving, and our NP0 value, again our NP0 is the total number of the electron concentration that were injected from the emitter to the base, is the value equals over here NP naught NP0 EVBE over VT. So we can put down this entire value over here to this point. Okay, right, so we can replace this value from here to here. So if I will do that, right, so IN, which is equals to minus IC, will be equals to AE Q DN minus NP0 EVBE over VT. So negative will be cancelled with negative. So let's call this as an IC now. So IC equals to AE Q DN NP naught EVBE over VT. I think I forgot the W thing here. So over W over W. So if I will compare this equation with this equation, I can see that EVBE over VT, EVBE over VT is the same. So this factor is proportional to the scaling current or the saturation current. IS equals AE Q DN NP0 over width. Right, so the take-home message over here is that the saturation current or the scaling current is proportional to all of these factors, where it is directly proportional to the area of the junction. It is directly proportional to the amount of the concentration of the charge carriers. So this NP naught, this was NP naught, right, which were minority charge carrier concentration in the base region, and then it is inversely proportional to the width of the base. Now, in more detail, this NP naught can also be rewritten as over here, coming from chapter 3 again, the fundamentals of PN junction, which is proportional to the charge carrier density to the doping concentration over here, right? So the value of the NP naught is proportional to the amount, the doping concentration of the base region, and this is also directly proportional to the intrinsic carrier density of the region. Okay, so I can also replace this value over here to get a new equation. So this is our final equation of the scaling current, We can see that from this equation, the scaling current is inversely proportional to the width. So if our width is smaller, our scaling current will increase. And it is directly proportional to the area of the emitter base junction. So greater the emitter base junction area, greater will be the scaling current. The value of the scaling current, if you remember from the PN junction diode stepper, is very, very small, up to 5 femtoamperes. Another important thing from the PN junction, if you remember that the scaling current is proportional or dependent on the temperature. For every 5 degrees Celsius rise in the temperature, the value of the scaling current usually doubles. We already talked about this, that the scaling current is directly proportional to the junction area. So if we will have, so that is why it's also called as a scaling current. This is also, I discussed it briefly earlier. Because it scales with the size of the device, right? So if we will have a device, if we have a larger device, right, its collector current will be larger as well. If we have a larger device, the scaling current will be larger and the collector current will be larger compared to a smaller device. Okay, so with that, this was the last topic and we are going to finish up our lecture today. So in a couple of minutes, I'm going to give you a summary of what we talked about. We started with a bipolar junction transistor. We talked about its basic structure. Three extrinsic semiconductor regions combined together. Emitter, base, and collector are the three terminals. It can be an NPN transistor and a PNP transistor. They are always emitter, base, collector terminals, right? So for an NPN, emitter is N-type and emitter is P-type. There are two junctions over here. One is emitter-based junction and one is collector-based junction. We talked about the modes of operation, 3 modes of operation. One is cutoff, active, and saturation. And the active and saturation are different regions over here as compared to MOS-FET, where active and saturation are exactly the same thing. In terms of operation, we talked about for active mode, emitter-based junction needs to be forward biased, collector-based junction needs to be reverse biased. And when we do that, we have a lot, because our doping of the base is smaller as compared to emitter, we have a lot of these injected electrons that flow from emitter to the base. Some of these electrons will combine with the holes in the base in a recombination process and neutralize. Rest of the electrons swept across the collector to base junction into the collector terminal. And what happens at the base terminal is we have these base electrons, base holes that were injected from the base to the emitter region. And then some of these holes are also drawn from the external circuit, the number of which is similar, is equal to the holes that were lost in the recombination process. Then we also figured out that all of these currents are proportional to this biasing voltage, VBE over VT. We derived the value of the collector current. This one, we also derive the value of the base current, which is proportional equal to IB1 plus IB2. And we saw that this beta factor was the ratio of the collector to the base current, so it was a common emitter current gain factor. We saw that this beta factor depends on the width of the base and the relative doping of the base to the emitter. We also derived the emitter current. We saw that the emitter current is proportional. Where is the emitter? Okay, so this emitter current over here, right? We also derived that this emitter current is the summation of the collector and the base current, and then we derived another factor alpha, which was equals to the collector current of the emitter current ratio. So this was a common base current gain, We're going to discuss that in more detail. Then we discussed the charge carrier distribution throughout the region. So with that, we are going to finish up our lecture today. And the next lecture, we are going to see some more circuit models. We will also do one example and discuss the saturation mode as well. All right, then with that, thank you so much. And I will talk to you in the next lecture. Bye-bye.